Okay. So let's go ahead and start. Maybe so I'll make a short introduction. Yet again, this is the time for our Industrial Engineering Department seminar series. We kick off this year's series with a presentation from Dr. Mehrdad Tamiz. He just joined Yaşar Üniversitesi's Industrial Engineering Department this fall semester. We're extremely happy to have him. He has a PhD from Brunel University and also worked for many years in the University of Portsmouth, I believe, and Kuwait University before joining to Yaşar University. His research interests include single and multi-objective analysis of real-life problems, specifically portfolio selection and analysis, logistics, and supply chain management. Today, he'll be giving a talk with the title Goal Programming with Extended Factors for Portfolio Selection. And I, for one, am looking forward to it because I don't know much about goal programming and I was always intrigued. So the floor is yours, sir.
Okay, thanks very much for your introduction. Yes, my interest in portfolio selection began many years ago. And in '91, I was exposed to goal programming. That's where I started sort of studying and understanding goal programming. And then we thought, oh, right, okay, portfolio, goal programming, they go together quite nicely. There's a well-known method for portfolio selection called Markowitz risk-return model. And basically, it's a quadratic programming model. And it's a single objective quadratic programming model. They usually fix the return that they desire or the risk that they desire and solve for the other objective. But in goal programming, we can deal with several objectives at the same time. So it's a really nice tool for portfolio selection and analysis. Basically, I started working in this field, as I said, back in '91. By about '93, '94, published a couple of papers in sort of goal programming and portfolio selection. Then I was in a meeting and I met someone from a Japanese bank in London called Nomura. And they invited me to give the same talk that the guy came to listen. So then my involvement with Nomura started in mid-90s, lasted for about 6 years. And we used a method that I'm going to talk about or briefly mention in this talk to develop a full portfolio selection and analysis system for the bank that was used until 2005, 2006. Anyway, so that, let me just go through the introduction of my talk. That was just a brief introduction to how I ended up with working in portfolio selection. Basically, in portfolio selection, we're dealing with stocks and portfolio. As you can see on the screen, there's a stock analysis. So basically, we're interested to find out how this particular stock or share is going to perform in the future, given its past performance. And then portfolio is basically concerned with selecting several of such stocks in order to depict the market that the stocks belong to, namely FTSE 100 in UK or Dow Jones in the US, etc., etc. And we're usually looking for an efficient portfolio. Okay, so efficient portfolio here, it says expected return is usually, oops, let me see, how can I go back to my previous slide?
You can either quit the presentation mode, go back and restart, or right click and go back.
Right click and go back. Okay. I can't see the
Top,
go back.
at the top, there's a previous when you right click, the second from the top.
Just click 2 and enter. 2, enter.
Previous.
Mehrdad. 2,
Yeah.
yeah, press 2 and enter.
2 and enter. Okay. Okay, thank you very much. Yeah, so we're looking for an efficient portfolio. So overall return is the same with a given risk. And so let me just go to the next slide. This is where Go programming comes into effect. I'll give you a very brief introduction into Go programming, what it is, and how useful it is as far as I'm concerned, or people in my field are concerned. If you look at the 3 constraints that we have on the screen, the first constraint less than or equal, then the second one greater or equal, and the third one equality. So what we do in Go programming, we turn constraint into soft objectives that are called just objective. So if you look at the first constraint, where the fkx is constrained to be less than or equal to bk, we add a negative deviation and subtract the positive deviation. So this always becomes an equality. And this particular objective is always satisfied. So no matter what the value of f and b are, you can tweak the value of n and p, so the left-hand side is always equal to the right-hand side. And from mathematical point of view, if you look at this objective, only one of the variables n and k can be non-zero, positive, i.e. the other one 0. So in this case, because we want the value of f to be less than the right-hand side value, I write the pk in red. That is what's known as an unwanted deviation. So if p is positive, then the f is going to be bigger than b, right? Because f has some larger value, you subtract p, it becomes equal to b. So that's why p becomes an unwanted deviation in this particular constraint. N is the wanted deviation. N is a good deviation, so to speak. If you look at the next one, which is greater or equal to b1, in this case, again, we add the n's and the p's to the objective, to the constraint, turn it into an objective soft constraint. N is called negative deviation and p is called positive deviation. Again, same thing applies here. This objective always satisfied, and in this instance, n is the unwanted deviation. Okay, because if n is positive, then that means f is smaller than n. So we have to add smaller than b. So we have to add the n. So the left and right hand side become equal. And in the third constraint, which is an equality, again, we turn it into soft constraint. We call it objective. And in this instance, both n and p are unwanted deviations. So the ideal value for n and p is 0. Both of them to be 0, so the f is equal to b. Now, we also, in the context of Go programming, we have an achievement function. This is where the sum of unwanted deviations are being minimized, as you can see on the screen. So all the deviational variables in red are unwanted, and we basically minimize them. So, and let me just say another thing here. We're talking about optimization. For the multi-objective optimization, the philosophy of optimization changes, because now in the field of optimization, the one of the main efforts is to find feasible solution. But in multi-objective optimization, we always have feasible solution. So the main effort is it goes into finding a solution that is acceptable by the decision maker. And what's known in the field is that it is always efficient. That's what we call it, efficient solution. Now, so here I have the full goal programming model. We are minimizing unwanted deviations, and as you can see, there are some sort of multipliers for the deviational variables. They all have coefficients. We have the alphas and betas, alphas for negative, betas for positive, and they're all divided by a k. K is a scalar that is used for balancing the problem. And so we have m objectives for this particular problem, and x in CS, that means we can also have hard constraints, just like a linear programming problem. And of course, all the decision variables are non-negative. And just one thing to say, it's quite technical. The Ks there are introduced in order for the solution of this problem 99% of the time to be efficient. So we don't bother with finding an efficient solution. Once the solver finds a solution for this particular problem, that solution is guaranteed to be, well, 99.9% of the time guaranteed to be efficient solution. Now, as I said before, Markowitz model, risk return model, it's a quadratic programming problem. So our first attempt in linearizing it, in using it, that we do not need a QP solver for it. We introduced this very simple goal programming model where we have the risk objective and we have the return objective. So as you can see, for the risk objective, the first one, we are minimizing the alpha. That means we really want to have this much risk or less, not more. The alpha or the positive deviation in this, the n, the negative deviation in this case is the unwanted deviation, hence it's being minimized. And in the second set of constraints, which is our objective function, which is the return objective functions, the unwanted deviation are the yes, for the risk, the P's are unwanted deviation, positive deviation. We don't want to go beyond what is acceptable level of risk. And for the return, unwanted deviations are the negative ones. So we want to achieve the return that we wanted to when we set up the model. And the sum of xj's equals 1. Basically, it's a standard constraint for any portfolio selection model. And that guarantees that all the funds are invested in the portfolio. So there's no cash left at the end of the investment. Also, Connor came up with an approximation model to Markowitz risk return model. That is, he came up with a linear programming model, which was equivalent to the Markowitz model. And this was again back in 90s. And it depicts Markowitz model very nicely. And there's hardly any difference between the portfolios that are obtained using Connor's model and the Markowitz model. And of course, Connor's model, because it's an LP model, much easier to solve. And we turn this into an equivalent goal programming as well, calling it Connor's GP, which more or less does the same thing as the LP, except it introduces that level of flexibility into Connor's model. It works quite well, so, but it can be improved, as you will see later during this talk. Now, different factors in portfolio selection other than risk and return. I had a PhD student some time ago, and she worked in the mutual fund field. And over there, they have several different factors that they consider for setting up a portfolio of mutual funds. And for her PhD, we developed several models using different factors, obviously, for the mutual fund sector to come up with mutual funds that were acceptable by the investors, mainly institutional investors. Then when she finished the PhD or about to finish the PhD, then we said, hey, just a minute, why can't we extend this into normal portfolio selection? So we came up with this idea of not just using risk and return, but other factors as well when we select portfolios. And of course, using goal programming, it enables us to have several factors, however many factors that we think is desirable. So we talked to some finance people, and we came up with 7 factors that is mentioned in here. Risk, obviously, the main one, return, the next one. Also, debt asset ratio. In this case, as it says here, we have a target value that obviously we want to achieve, but to return. Okay. But at the same time, we have to minimize the unwanted deviation for this case. The next factor is the earnings per share. These are the sort of things that finance people thought were important in selecting portfolios. So that's why we actually decided to make our experiments using these factors. So again, the right-hand side value is given there, and we minimize the unwanted deviation variables, in this case being the negative deviation. Then we looked at price book value, or PB for short, get a target value for that, and minimize the unwanted deviation, the negative deviation in this case, and operating cash flow ratio. These are all the factors that are readily available in financial markets. All you need to do is just sort of log into the particular database and get all these numbers for the last however many years that you wish. And they are freely available. You don't actually need to pay for them, which is a bonus for us academics. And the last one is dividend yield, which some people may consider very important, because you not only get return on your portfolio, not only the share prices increase, but you also get dividend, which is considered as a further bonus. So we use these factors, 7 factors. There's the model, nice and simple model, not difficult at all to solve. It's not a large scale sort of goal programming model. But of course, the philosophy behind it is quite important, and that's what we were concerned with. So as you can see, we are normalizing the model. All the K's are basically the right-hand side values, and the alphas are the weights that decision makers sets on the unwanted deviational variables, and the N's and P's are the unwanted deviational variables. So we have all the 7 objectives there, plus the sum of xj equals to 1, which means we have to invest all the cash into the portfolio. So there's the model, which on the face of it, it looks simple. It is simple, but of course, a lot of thought went into developing the model. As I said, we got ideas from the mutual fund sector in finance. And we experimented that using the Dow Jones data that was readily available, and came up with the results, as you can see on the table. I'm not going to go into these numbers in details, but you can see on the table we have various portfolios. The first, the second row is the number of stocks that is selected. Again, this is a field in itself, because if you have more stocks in the portfolio, you have to pay a lot more transaction costs, because you need to purchase these things, you need to sell them, you buy them at a higher price, and you sell them at a lower price. So there's that transaction cost that ideally you want to have as few stocks in your portfolio as possible. And then we have the overall risk, which is measured by the model itself, the overall return, and then we have the sum of deviations from the Dow Jones. In a way, that is the sort of the risk of the portfolio. That's what we consider as risk of the portfolio, because you have the Dow Jones index. These portfolios pick shares from Dow Jones index, which has 30 shares in it, and then they're supposed to track Dow Jones. They're all sort of passive, what we call. We're not trying to beat the market, but follow the market. That's what most financial institutions wish to do, which is surprising, really, but that's their wish. So then the experiments, two-factor models, basically Markowitz, Connor, and the GP, the first GP model that we produced, developed, that simply had risk and return factors. Then we have the extended factors. We divided into several different groups of experiments, as you can see there. Unbiased weight, biased weights, basically unbiased, they were all one. There was no difference between the deviation of any of the objectives, any of the factors. And the biased weights, we set those weights ourselves. So we thought maybe dividend is more important than the other factors, so we gave it a higher weight. And of course, in real life, the fund manager, the person that is going to invest people's money in portfolios, he or she will decide these factors, i.e. which factors to use and what weights to give to the unwanted deviations. And then if you look at the table closely, you see that extended factors overall do better than Markowitz, Connor, or the two-factor GP model, both in terms of return and risk. So we were quite happy with the results, and we immediately published it or submitted for publication. In fact, this was the very last paper that I published before I sort of retired for the first time in 2017. Okay, so that basically brings me nicely to the end of my presentation. And now I'd like to answer any questions you may have. Before actually that, let me just say one more thing, that there are methods, there are ways of improving this, and I'm talking with colleagues in Yaşar right now in trying to improve this and hopefully come with better methods, especially in the risk assessment part of the investigation, and hopefully be able to publish more papers and maybe even improve the models. As we say in the conclusion of our paper, our results, i.e. the ones you see on the table before you, they're not by any means conclusive. They don't actually prove that our method is much superior to other methods, but it's a method that, if you like, is more realistically depicts the real world, where fund managers are concerned with selecting portfolios and, of course, rebalancing portfolios. When it comes to rebalancing portfolio, the number of shares are quite important. As you can see, the models with extended factors, the most number of shares we have is 7, whereas if you look at Connor's model, there's 24 stocks there. But of course, Connor's model manages to follow the Dow Jones better than some of the extended factors, and the return is also reasonable, although extended factor models, some of them offer better returns. Okay, I finished now. Thank you very much for listening.
Well, thank you very much for your presentation. This is definitely very interesting. At this point, of course, we would like to ask the audience if they have any questions. And I sure do have one question, but I'll give the priority to our guests and attendees first, and then, you know, if it's not asked, I will have a question myself.
Well, may I start?
Yeah, I think so. Go ahead.
Well, thank you very much, Mehrdad. But Chair, I have a couple of questions. If you go back to your formulations, where you introduced the formulations, well,
Where?
I'll try the very first slide when you introduced the wanted and unwanted deviations. Yeah,
This one?
yeah, this part.
Yeah, yeah.
So just my question related to understanding this goal programming concept. So this f of x, which you list as constraint, actually can be represented as an objective for an original problem. Then you somehow convert with a target level of this objective, you convert this one into a constraint, and then by the manipulation of negative and positive deviations, you know, you make sure that it is satisfied. Did I understand correctly?
Yes, they're not necessarily objectives. They could be constraints of any type. So what we do, we take the constraint and we turn it into a soft constraint by introducing the deviational variables n and p. So in other words, as I said, the entire philosophy changes now. We no longer look for sort of satisfying solution, if you like, a feasible solution, but we look for good solution amongst the feasible, because they're all feasible now anyway. And yes, so the Fs, they can be constraints or they can be objectives. So the right-hand side values, they are values imposed by the decision maker to say, you know, I'd like to spend not more than so much for my operation. Yes.
But
that is.
In the goal programming, can you have constraints which are not in this relaxed form in addition to these?
Yes.
Can you have, yeah, you can have, right? So
I'm
trying to relate, I try to relate your portfolio selection problem with this for goal programming formulation. So yeah. F of X can be risk, another F of X can be return, and so on.
Yes,
right?
of course.
So,
of course.
you know, so I may have a single, you know, formulation for minimizing risk. I have another formulation for maximizing the return, or, you know, whatever the other metrics I consider. I have separate formulations. So now I want to combine them all. So I take those objectives in those separate formulations into a form of constraints, and I want to wanna use the deviations as the objectives. That's what I understand from your description.
Yes, you're quite right. I mean, the terminology is different. I mean, the deviations, as you can see here, they're minimized in what we call achievement function. We don't call it objective function. But nevertheless, all the constraints, all the hard constraints, whatever they can be return, risk, whatever they are, man hours, they're turned into soft constraints or objectives, and then unwanted deviations minimizing the achievement function. That's what we do in goal programming, basically.
Okay, thank you. And my second question is, in your when you start your presentation, you said that portfolio selection problem is a good fit for goal programming. So it's a good match, you said. So therefore, you proceed with that.
Yes.
So
hello?
What else can be a good fit for goal programming in terms
You're
of?
frozen.
Oh, am I?
Hello?
No, actually, no. I
Sorry,
think your
you
connection.
were frozen. I didn't hear the question. Can you
Okay,
repeat,
you know,
please?
okay, I'll repeat my question.
Please.
You know, since your portfolio selection problem is a good match with the goal programming solution approach or
Yes.
formulation approach.
Yes.
You know, what kind of other problems can you you know, name as a good match for solving with goal programming?
Well, I tell you what, in our field, obviously we are quite biased. We think that all problems have multiple objectives. So what analysts or academics or practitioners do, turn them into single objective and then solve them, whether linear, whether nonlinear, convex, non-convex, stochastic, deterministic, whatever. So that's what we believe. So any field, any problem that you could think of, we believe is multi-objective. So they can be used in several things: diet planning, manpower planning, in product selection, anything, any problems that you have, we believe is multi-objective. And they can be solved using one of the methods or methodology of multi-objective methods. Well,
then I would simply you know, request from the professors of our department, the faculty members of our department, to use this goal programming approach in the senior design projects of our students this year. Probably, you know, they can get help from you, or we can get help from you for formulating those problems as you know, multi-objective or goal programming.
Yes, of
and
course.
My final question is there an extension of goal programming where you incorporate randomness in the formulation?
Yes, absolutely. Stochastic goal programming, there's a lot of people working on that field right now. In fact, I'm giving a talk later today at 6 o'clock to some graduate students in Qatar University that are using stochastic GP. So we're just going to discuss some problems with them. So yes, there is, and it's quite strong. And we can deal with that in the context of a multi-objective approach, yes.
So it lies in your interest of research, right? So
I am interested, but not passionately interested.
Okay. So maybe sometimes later we can have a another talk about that stochastic goal programming.
Yes.
As an introduction.
Yes, of course.
Thank you very much. I'm done, Mahmut.
All right. No, thank you. Any other questions from the audience? Let me go ahead and ask, and if there are any other people, as the host, I didn't want to ask first, but kind of goes to the same point that Özgür Toy Hoca asked, but I was going to ask if there how do you incorporate uncertainty and randomness? And the reason I ask that is, while I was listening to this, I was also thinking about applications of wall programming, which I didn't really know much about. And it's very nice and cute, the formulation. I like it. And I think I understand the basics. Recently, there's, of course, when you have uncertainty in a problem, and a lot of real life problems that I deal with also have uncertainty. There are a couple of ways to deal with that. And one of them is stochastic optimization, which I'm farther away. But I've been thinking about how to handle those uncertainties, especially in production environment, where we are working on a AGV scheduling in a production shop floor. And there, I'm more interested in now finding a more robust solution, and the robustness is, defined in a number of ways. We are trying to come up with an improved version or definition of robustness instead of a strict robustness. So the question was how do you incorporate those kind of uncertainties, when you do, how do you solve that? Which I kind of got my answer, but I'm going to look into if there's any application of this into a production scheduling planning environment. And that could be interesting, because there you have these certain uncertainties and objectives that can be made soft, as I understand it, with these negative deviations. So you can be a little bit late. It's not the end of the world. You don't want to. You want to minimize that, but the idea applies very nicely. All right. So because those kind of problems that we're dealing with mathematical modeling, they get very big very easily, and they get very difficult to solve. So this way, as I understand, it will be actually easier to solve this version of that. So that's something that I want to maybe hear your thoughts about, or if you know of applications, or if not, then we'll discuss maybe further along later on.
Yeah, sure. I mean, when I talked about Markowitz model, his risk measurement goes into standard deviation, which clearly is quadratic, non-linear. And then Connor took that approach and linearized his Markowitz way of measuring risk. And he shows in his paper, I can send you a copy, he shows that his linear measurement of the risk is more or less the same as the standard deviation measurement of the risk that Markowitz uses. So yes, it is possible. And there's lots of ways of dealing with this. Right now, I don't know of any, but I'm sure we can sit together and find references that are useful for your particular field.
Well, thank you very much.
Sure.
Are there any more questions from the audience?
I have, Mahmut Hocam.
Yeah, please go ahead.
Actually, my question is about the same topic, the risk. Mehrdad Hocam, can we go to the first model, the Markowitz model, I guess, that you showed us? Yeah. This one. Yeah.
Okay.
Although it looks like linear, I think it is non-linear due to the risk term, right? If we measure the risk based on standard deviation and covariances. So if that's the risk term, the variance or the standard deviation, including the dependencies between the securities here, is this an easy problem? I mean, in quotation, or when we increase the number of items here, how can we solve this problem?
Yeah, I mean, this here we're dealing with 30 assets, 30 stocks. Dow Jones has 30 stocks only. And then the risks, they're actually calculated for every sort of asset given its movement in the previous period. So basically we take, I don't quite remember exact time period, but we take something like 6 weeks of data to measure all the risk and return and all that. And then we use that 6 weeks to produce the portfolio using this model, and then use another 3-4 weeks of data to examine, to test the results, to see how close they are to the actual index. So this is a very crude measurement of risk that we've done. So they're basically the standard deviation, the REs, the values of the standard deviation at that particular time period for that particular stock. Okay, it's a very crude measurement of risk, but nevertheless it can be done. And as you saw in the table of the results, the portfolios achieved are not that bad. They are similar to Markowitz. Okay, so
I think, as far as I understood, this formulation assumes that the assets are independent from each other.
Yes.
Their prices, their
Yes.
returns.
Yes, yes. I mean, technically, they could be, because they belong to different companies for sure, but maybe they follow more or less the same path because of the market situation. But having said that, I mean, various sectors do better than others for different market conditions. So they may not, I'm contradicting myself, I know, they may not follow the same pattern, but that's precisely why we, as a measure of risk, we use the standard deviation, and we basically calculate it for that particular stock for that particular period. And then using that and the return obtained in that sort of period, then we put them all together and come up with a portfolio. Yeah.
Okay. Thank you, Hocam.
Sure.
Any other questions? Well, this was definitely very interesting, dear Mehrdad Tamiz. Thank you very much for your presentation. I think there are no other questions at this point, at least. There might be others, and people can reach you. You're here now. So thank you very much. I'm going to close this first session of Industrial Engineering Seminar Series at this point. Thank you for everyone for attending, and I think thanks to our presenter.
Thank you very much. Thanks for listening.
Yeah. Bye-bye now.
Bye.
Thank you.